So, this is what is the main body of the code, but, and there are a few buts, there are some more points to discuss. First thing you want to say that typically for the Lennard-Jones interaction you can choose dt equal to 0.005, and by convention in most cases one can also take m to be 1. So, what does this dt equal to 0.005 mean? I mean, what is the unit of time? We will discuss it, it has to wait, I cannot discuss all the things at once. So, we will be discussing units, but typically if you have Lennard-Jones with epsilon equal to 1, dt equal to 0.005 works pretty good. And what does pretty good mean? We have to run the code, look how well energy is conserved, if momentum is conserved, and so on and so forth. One typically chooses m equal to 1, but there are these quantities like dt into dt into 0.5 by m. So, there is no point. So, when you are doing this calculation, right, there is no point in writing it like this, because this calculation dt into dt by m into 0.5, we are doing it all the time in each of these iteration, and all iteration, when I mean I equal to like 3 into n part, every time it is doing this algebra, and you are doing it so many times over n iterations over every time step. Instead, if you basically replace this quantity by some other variable dt2 dt square by 2, say dt, so you can write it like this, dt square by 2. You can at least remember it right at the beginning of the code, and here like you have 0.1 0.5 half by m into dt. If you basically write this as dt by 2 right at the beginning of the code, outside this loop essentially, right, then you save the computer time, because the computer does not have to do this multiplication every time. You might think, okay, to do a multiplication it takes with gigahertz like 1 nanosecond or something like that, but then you have a large number of particles, you are going to calculate distances, you are going to do this for a large number of particles over multiple iterations. So, finally, this takes time, and every time it is doing a calculation, this is like 3 multiplications, 1 division, it takes time. So, you should just replace these by suitable variables. So, these details, the molecular dynamics are important, you do not write it like this, right. The other thing is, okay, even before we go to the body of the so called MD code, when n equal to 1, that is the first iteration, you need the velocity of the particles, you need the force of the particles, and you need the position of the particles. So, what have we not discussed here? Initialization. How do we initialize the position of the particles, the velocity and of the particles? If you know the position, you can calculate the force, because force depends upon the distance between the particles, right. So, even before we come to the body of the MD code, we need to discuss initialization, right. So, here is essentially the body of the code. Here basically the program mod11 starts, here it ends. But before that, we have to define suitable variables, and these variables can be read. You can give them on screen, or you can write them on a small separate file, and you have to define definitely Lx, Ly, Lz. Typically, at least for the beginning, you can choose to be a cubic box. So, all 3 directions they have the same size, and so Lx equal to Ly equal to Lz. You have to choose n part, the number of particles. You have to choose the value of R cut or Rc, which is the cutoff distance of the potential. Write it, you have to explicitly mention it, and once you have your value of the Rc, then you can calculate the so called Fc, what is the value of the force at the cutoff, and then you have to calculate also V dash C, V the potential, the value of the modified potential at the cutoff. Those are quantities which you do not need to calculate every time you calculate the force, because those are fixed values. You want to save computing calculation time, right. So, as soon as you have access to this quantity, you calculate the value of Fc, you calculate the value of V dash C, which you are going to use later whenever you calculate the force. Other than that, you have to mention the how many iterations, you want to run your code for. That will depend of course upon the physics that you want to extract from the system, how many iterations, how many independent runs you need to run. That once you are running an MD in a regular manner, you get a hang of that. But anyway, for testing you can choose it to be 1000 not 1000, 10,000 iterations, 1 lakh iterations, 10 lakh iterations, just as we were doing for molecular, for the Ising model. Then you should could initialize the random number generator, you might need it, and you can need it even to initialize the position of the particles and the velocity of the particles. So, how does one initialize the position of the particles? Suppose this is your simulation box of size Lx cube, assuming Lx equal to Ly equal to Lz. Your final physics, your final distribution of particle positions and the velocities of these particles is not going to depend upon your initial position. Just like in Ising model, you can start with any initial configuration. The easiest would be to you put all the particles, you put all n particles at equal distances from each other, and once the force starts acting, and since they have initial velocities, of as soon as you start the molecular dynamics, of course they are going to move around in space, and how they are distributed, whether they are clumped, whether they are all far apart from each other, on an average will be decided by the potential, the density, the temperature, the thermodynamic quantities. But just to start off, you can just put them all at equidistance from each other, say at a distance of, I do not know, 2.3, or depends upon the density also. If it is highly packed, you can't fit all the particles of the box. If you start with distance of 3, each particle is surrounded by neighbors which are at a distance of 3 sigma. So, here distances, as I said in the last class, is measured in units of sigma. So, you set sigma equal to 1, the diameter of a particle equal to 1, and when you mention Lx, you say, okay, my simulation box is 50 times the diameter of a particle, right. So, that has been assumed. So, when I say that the distance between any pair of particles in the initial condition is 3, I actually mean 3 sigma, where sigma has been set equal to 1. Okay. So, that's a possible initial position, is basically sitting on a lattice. Of course, the lattice is going to melt or not melt depending upon the potential and the density and the temperature. So, or it could go into some other crystalline form. Here I am just talking about a simple cubic lattice. One could always start Lennard-Jones simulations from a lattice simulation, or you could choose, well, you know that you do not find that comfortable, you can choose put particles randomly in the box, you generate a random number, generate and multiply it into Lx, it will be some number between 0 and Lx, and you say, okay, I shall place the first particle at this x coordinate, and you generate another random number, multiply it by Ly, and that will be another some number between 0 and Ly, which is basically the size of the box. And you can do similar things for the z coordinate of the particle, and you say that okay, I put it randomly somewhere inside the box. But when you put the second particle, you should ensure that the distance of the second particle and the first particle is greater than sigma, because if you by chance you put it right on top, because you are using a random number generator, you put them right on top of each other, right, that would lead to extremely large forces as soon as the simulation starts. So, typically when you put the second particle, you do not have any problem. Typically the random numbers which are chosen, you can put it some other point in the simulation box, but as you put more and more particles, there is larger and larger probability that one of the particles will sit on the top of an already introduced particle. So, if you want to basically introduce particles randomly, we want to place particles randomly in a simulation box, then you have to take suitable precautions. You have to write a code and check that when you are introducing a new particle, one of those n part particles, that they do not overlap with a previously already introduced particle, right. You can do it or just put all the particles on a lattice at suitable distances, anyway the lattice will melt, at least if you have Lennard-Jones particles and you have significantly high temperature, right. So, that is how you initialize the position of particles. If you are introducing Lennard-Jones particles, is relatively easy, but you might also be ending up introducing or wanting to study more complicated systems. Suppose a rod like molecule, right, or a polymer. What is a polymer? You have a polymer base where basically the monomers, the particles which constitute the polymer, right, the monomers, assume them to be spherical and they can be connected by springs. So, you cannot necessarily in this case choose the position of n particles randomly, because the constraint that the distance between neighboring particles on a polymer along the polymer chain, they should be at a distance of approximately the bond length, that has to be maintained, right. You cannot say that, oh, a bond is extremely highly stressed, that is unphysical. So, typically you say, okay, the first particle is here, the second particle is here, the third particle is here, you put them basically keep on incrementing the position here, but then you have to be sure that the fifth particle basically sits here and not here, because then this basically this bond would be extremely stretched, and if it is extremely stretched, then the force acting between these two particles is extremely high, and then when you start the simulation or you run the iterations, the extremely high forces can lead to a breakdown of the integration, unless you choose extremely small values of dt, which you do not want to do, right. So, for Lennard-Jones, introducing particles is simple. If you have more complicated systems, you might have to take care how you want to introduce the particles, but let us stick to the simple case. I just gave you a caveat, a warning that one has to be careful. Lennard-Jones is relatively easy. Introducing the velocity, well, you could say that each particle is moving in random directions right at the beginning. So, you do not want to give all the particles the same velocity, they can't be moving in a perfectly the same direction, that would be again unphysical. That is something like all particles moving as a whole. So, this it is moving, it is like a river where all the particles are moving, unless you want to actually simulate that. But let us first of all consider a static liquid or a gas. How would you model that? Because that is simpler. If you are modeling flows, that is more complicated. We will leave it for a future class, or basically if and when you need it, you can always learn that aspect. So, in general, you want the velocity of all the particles to be in random directions, more like what you have the gas particles in this room, they are all moving in all possible directions. But remember, they have also in equilibrium the Maxwell-Boltzmann distribution of speed and velocity, right. For simplicity, you can say that what, I want particles in random directions, but I am choosing their velocity from a uniform random number generator, and as the particles move around in space, they collide with each other, and if they are doing the right physics, if we have modeled the right physics, then we are going to generate basically a Maxwell-Boltzmann distribution. In fact, that is going to be one of our tests that we are doing our molecular dynamics simulations correctly. Okay. For simplicity case, you say that okay, I am using a random number generator here, right, which generates random numbers between 0 and 1. Okay. The velocity of each particle is some amplitude, which we will discuss how you choose that amplitude, into random number minus 0.5. Random number minus 0.5, what does it do? So, random number would choose a uniform random number between 0 and 1, and if you subtract 0.5 from it, then basically the range of that random number becomes minus 0.5 to 0.5. So, you choose any random value You choose that to be Vx, you choose another one to be Vy, choose generate a third random number, and from that generate Vz. So, some particles will be moving in the positive direction, some particles will have velocities negative values which is moving in the negative direction. So, on an average you essentially have equal number of particles moving right, equal number of particles on an average moving left. That is how you start off. Then you have to ensure that your momentum in the x, y and z direction goes to 0, because if it is not exactly equal to 0, that means you have a box, you have a simulation box which has a center of mass velocity, which means it is moving. You want to look at a stationary liquid, right. So, after introducing the velocity of all the particles, you calculate the center of mass velocity of all the particles and subtract a certain small amount, that exact amount, from the velocity of each particle. So, that the center of mass velocity of the n particles becomes exactly equal to 0, right. You have n particles, half of them are moving to the left, half of them to the right, some on towards the camera, some away from the camera, some upwards and some downwards, Vx, Vy, Vz, and it goes from minus f minus 0.5 to plus 0.5. The question is, what should be the value of A? Some amplitude. There is no reason that it should be just simply you choose it from minus 0.5 to plus 0.5. In fact, the way you have to choose it is, once you have specified the temperature of the system, right, you know that the equipartition theorem holds half mv square average equal to half kBt for each degree of freedom. Basically, the value of A should be such that the average V square of n particles for each degree, Vx square average over n particles, Vy square average over n particles, that should be equal to close to half kBt, right. That is what I have written here. So, half mvx V square, or rather if you just take one particular degree of freedom, half Vx square should be half kBt by m. I mean, m could be here and then, and m you can choose even to be 1, right. So, you want to choose a Vx, so that the average kinetic energy of the system is approximately half kBt, and this condition essentially determines the value of A. So, how do we do it? So, we have to calculate the expectation value of Vx square. What is V? Vx, say, I mean one component is r minus 0.5 into and some amplitude A, and that is exactly what we have to determine. And if you have to calculate Vx square average, because where n is large, we are generating so many different random values of Vx, and similarly for Vy and similarly for Vz, that if you average over all particles, you will have fairly good distribution. So, you can take average Vx square over the particles, right. So, basically this Vx square can be written as half mv square, half 0 to 1, because that is the range of minus 0.5 whole square into A square, and that should be equal to half kBt. So, half of this factor cancels, and what you have is 0 to 1 A square. I have just expanded this, r square minus r plus 0.5 whole square is 0.25 dr. Basically, you are integrating over the entire distribution of random numbers. So, that is why 0 to 1, that is your range. So, r being the random number, and that should be equal to kBt by m, right. And if you work out the algebra here, and I have worked it out from here for you, if you integrate it, it becomes r cube by 3 minus r square by 2 plus 0.25 r 0 to 1, and that should be equal to kBt by m. And if you work this out, you essentially get A equal to root 12 root kBt by m, and that is how you choose your amplitude of A. Amplitude of the velocity, so that when you start out, your average velocity over n particles remains close to kBt. whatever value of kBT you have chosen. Okay, so now you have we have discussed initialization of position, we have discussed initialization of velocities. Since you have positions, you can call calc force, calculation of force, and you have the initial forces acting on each of these particles, and now you are all set and nearly ready to basically go into the so called body of MD, except that you still have some things to learn, and that is the following. As the particles start to move, you have a simulation box, you have to either implement walls, so that once the particle suppose is moving and this is the end of the simulation box, when it goes, it hits, it should come back into the box. But often when we are studying liquids, we are basically studying practically an infinite number of particles, n equal to 10 to the power 23. We are studying the system in bulk, if you like, and if you implement walls and you have some 1000 particles, then there will be strong wall effects. Rather, you want to study a system where all the particles are surrounded in all possible directions by identical copies of the system, so that you don't see confinement effects. I think we discussed this similar stuff even for the Ising model, right? You want to basically simulate the system in bulk, so that in each direction you have an identical condition. There is an endless chain of endless number of particles whichever direction you see, and that basically brings up the discussion of periodic boundary conditions, where you say, okay, even if the particles go out from here, they come in from the other side of the box, right? Or else you could model walls, and modeling walls is a pretty detailed topic by itself. By having explicit walls, you could basically confine all the simulated particles within the box, and people do it. Especially when they want to study nanofluidics, or you want to see systems in a nano confinement and so on and so forth. However, if you want to compare with classical statistical mechanics, where you do not have confinement, then you would rather be well off studying systems in bulk, and then one would be better off using periodic boundary conditions. So, we have to discuss that. The other point is basically that as particles start to move, from their initial position and velocities, depending upon the interaction between particles, they would increase the potential energy of the system or decrease the potential energy, and similarly correspondingly the kinetic energy of the system also changes. The average kinetic energy, because the average kinetic energy of the system also changes, because if the potential energy decreases, suppose there is an attractive interaction, all the particles come close together and sit at the potential minima, then the potential energy decreases. To keep the energy constant, the average kinetic energy of the system has to increase, which means that the particles are moving around with higher speeds, and half mv square average is equal to half kBT. So, if the average kinetic energy of the particles have increased, then what you have is essentially that the temperature of the system has increased. But you wanted to study the system at a particular temperature which you want to decide, right. So, what we need is the concept of a thermostat. Thermostat is something which will keep the average kinetic energy at a value, so that the temperature is maintained. So, that half the 3 by 2 n kBT equal to half mv square, your equipartition theorem, which means the thermostat will either take energy out from the system, readjust the kinetic energy of the system, or put in energy into the system, right. That is exactly what you have in a canonical ensemble, right. So, energy is lost or energy is gained, there are energy fluctuations. So, we must introduce a thermostat if we want to study a system at a particular NVT. If you do not have a thermostat, then what you are essentially studying is NVE ensemble, where the number of particles, the volume of the particles and the energy of the particles is constant. And the physics of the problem of course decides which ensemble you shall choose. We shall discuss both NVE and NVT. Okay. In today's class, we will basically discuss the periodic boundary conditions, and thermostat shall be discussed in the next class. And so, how do we implement periodic boundary conditions? Why do we need? Suppose this is a particular particle, you have updated its position, there are some forces acting on it and its position gets modified, it gets updated and such that the position of the particle is larger, it goes out of the box, and then you must put it back. You should basically put it back here, right. So, because it was out of the box, and that is basically should put it back here. Similarly, if a particle goes out from the top, so it is again the position of the particle is such that the value of, suppose the y coordinate value is greater than Ly, then it should be put back into the box here, because this is basically put it back from the other side. And similarly, suppose a particle is position gets updated, so that it moves to the left, position x coordinate decreases and becomes less than 0 even. You imagine the box is from 0 to Lx, 0 to Ly, 0 to Lz, but suppose its position is such that it becomes less than 0. It depends upon the value of the force and the velocity, of course, the magnitude and the sign of velocity and force. If it becomes less than 0, then it should be put it back here. How do you implement that? How do you implement PBC? You basically if the position, after the position gets updated, let us look at that. So, here. So, your position update was happening here in the main body of the code, and after its position gets updated, here you write down the conditions to implement PBC. And what do you write down? You write down precisely this: if position is greater than Lx, which means the position of the particle after update is here greater than Lx, then pos I equal to pos I, means the ith particle. Actually, you are also mentioning whether it is x or y or z, it is pos I minus Lx. And if you are doing position y, if you choose the size of the box, so that in 3 different directions Lx and Ly and Lz are different, then you have to be careful whether you want to subtract Lx or Ly or Lz. But if you take a cubic box, you are safe. It's just for the sake of learning, and then basically Lx equal to Ly equal to Lz, then it does not matter, right. And if on the other hand some particle goes out here or goes out here, or rather this way, then if pos I is less than 0, then pos I equal to pos I plus Lx, which means it has gone here. We are subtracting the length of the box and it will sit here, whereas if it goes out from here, you are adding the length of the box. So, you are basically adding the length of the box and it is going to sit here. So, as a consequence of periodic boundary conditions, what you have? You essentially have your main simulation box, which is drawn here, and as the particle goes out, right. So, maybe from here, right. So, that it can sit here, or you could just put it back here. So, this putting it back here is the same as putting, I mean, if it goes out, you are putting it back here. That is what the PBC essentially does, is that the main simulation box is surrounded by identical copies of the same box in all possible directions. So, hence you are seeing this system in basically bulk, because in any direction you have essentially statistically similar systems. Of course, the size of the box should be significantly larger than the diameter of the box, and especially if you are near critical point, there could be correlations, and these correlations could extend to infinity. So, one has to be careful, of course, but if you are away from the critical point, which is the case we shall study in this case, basically correlations between positional correlations die down between 4, 5, 6 times the diameter of the particles, and if size of the box is suppose 20 or 30 or 50 sigma, then essentially statistically you have self similar systems surrounding the mean simulation box. Right. With that, we shall end today's lecture, and we shall discuss the other point of thermostat in the next class. Thanks.